Hello, everyone, and welcome to the Parsons Technical Webinar Series. I'll be your host today, Jessica Bennett. Today we have with us Natalia O'Connor presenting on reductive defluorination of PFAS using an ultraviolet light photochemical reactor. We can go to the next slide. We'll go over a few housekeeping items first. We'll be keeping all phone lines muted throughout the presentation until the Q&A session at the end. If you have a question during the webinar, you can put it into the chat feature at any time, or you can hold it until the end to either ask live by raising your hand or putting it into the chat. This webinar has been approved for 1 professional development hour credit, or PDH. If you would like to receive a PDH certificate, you will need to download the attendance form that will be posted as a link multiple times during the webinar and answer 3 multiple choice questions. We will also post those questions in the chat in case you have any issues accessing the form during the webinar. And as always, if you have any questions or concerns getting this form, please send us an email to danielle.savin@parsons.com. And finally, this webinar is being recorded and will be available on the Parsons YouTube channel in the coming few days. So just a quick agenda for today. We'll introduce our guest speaker, followed by a core value moment before we get into the technical presentation, and then wrap up at the end with the Q&A session. So a little bit about Natalia. She is an R&D scientist with us at Parsons. She has a master's of science in chemistry and chemical engineering and 5 years of experience in environmental R&D, specializing in remediation and analysis of legacy and emerging contaminants such as PFAS.
Thank you, Jessica. I'm Natalia O'Connor. Thank you, everyone, for showing up today for this presentation. And before I jump into the presentation, I would like to briefly touch on one of Parsons' 5 core values that are incorporated into all the work we do. And today, I would like to focus on the core value of sustainability. Under the core value of sustainability, this presentation focuses on green remediation, which is the process of examining the environmental footprint of site cleanup activities and taking steps to minimize the footprint. Per- and polyfluoroalkyl substances, or PFAS, are a widespread global issue due to their high mobility, recalcitrance, and associations with negative health effects. Parsons is focused on developing PFAS degradation methods that achieve effective destruction of PFAS with minimal energy requirements, greenhouse gas emissions, and waste. As for the agenda today, I will start by giving an introduction on PFAS and remediation technologies, followed by an introduction on the use of catalyzed UV processes for PFAS destruction. I will then present our initial lab development studies focused on our engineering and then followed by our chemistry investigations, before concluding with the validation of our catalyzed UV technology on the destruction of PFAS in complex matrices, namely a highly contaminated aqueous film-forming foam impacted rinsate. So per- and polyfluoroalkyl substances, or PFAS, are a class of alkyl compounds classified by their high proportion of carbon-fluorine bonds. There have been over 9,000 PFAS identified, with many more entering the market daily. PFAS are often classified into different groupings based on context, including the synthesis method in which they are made, for example, electrochemical fluorination versus telomerization. There are functional head groups such as carboxylates, sulfonates, ethers, and betanes, some few pictured here. There are applications such as their use in firefighting foams, personal care products, textile finishings, or industrial processes. Due to the recalcitrance and widespread transportation into the environment and biological systems, PFAS are often referred to as forever chemicals. The highly recalcitrant nature of PFAS is due to the presence of the very strong carbon-fluorine bond all throughout the molecule. The carbon-fluorine bond is the strongest bond in organic chemistry, which makes PFAS very difficult to destroy. The recalcitrance of PFAS is also affected by several factors, including the carbon chain length and the degree of fluorination, per denoting fully fluorinated molecule versus poly denoting a partially fluorinated molecule, and the functional head groups. PFAS can also transform during remediative efforts, further complicating treatment. There is a need to destroy PFAS in water, ensuring that the only remaining products are inorganic fluoride and other innocuous byproducts. One technology that is particularly promising to achieve this involves the use of UV-activated photochemical reactions. So how do we utilize our ultraviolet light? Ultraviolet light photochemistry uses high energy photons to initiate chemical reactions. Generally, these chemical reactions can initiate synthesis reactions or the creation of molecules, or they can initiate the decomposition reactions or the destruction or degradation of molecules. UV light alone can be used to destroy several pollutants, including organic dyes, pharmaceuticals, and pesticides. However, UV light alone cannot destroy PFAS. UV light can be used to activate several different photosensitive reagents, allowing for the use of oxidizing or reducing radical chemistry. And in brief, oxidation chemistry involves the removal of electrons from organic molecules, which is effective for the destruction of perfluorocarboxylic acids and the fluorotelmer classes of PFAS. And reduction chemistry involves the addition of electrons to organic molecules, which is effective for all classes of PFAS compounds. Several previous scientific publications have investigated the use of single photosensitizer systems for the destruction of PFAS in water. During my graduate studies, I investigated different single and multi-photosensitizer systems to achieve the complete destruction of PFAS. Of the 3 photosensitizers I investigated, I found that sulfite and iodide together were found to be the most effective, demonstrating 99% destruction of PFAS in a small-scale benchtop batch reactor system. Since joining Parsons in 2024, I have been fortunate in continuing this work through the Internal Research and Development Program, or IRAD, focusing on novel developments in leveraging the synergistic UV photochemical reactions to effectively destroy PFAS, and transitioning away from simple batch reactor systems to more optimized flow-through treatment systems. The patented catalyzed UV technology, which I will be presenting today, focuses on unique emergent radical chemistry that occurs when activating sulfite and iodide together with UV light in the presence of other reagents. One of the challenges when working with a multi-reagent photosensitizer system is understanding the synergistic chemical reactions present. In a UV-activated sulfite and iodide system, the iodide acts as the primary photocatalyst, which allows it to convert photons into aqueous electrons through a charge transfer to solvent process. In our catalyzed UV system, aqueous electrons are the primary radical of interest, as they are responsible for initiating the breaking of the CF bond and PFAS destruction. In the UV activation process, the iodide anion is converted into an iodide radical, resulting in the generation of an aqueous electron, but losing its photocatalyst properties. To overcome this, we can use sulfite, which acts as a sacrificial catalyst, allowing the iodide radical to regenerate back into the iodide anion and restoring its photocatalytic properties. Sulfite also acts as a secondary photosensitizer, generating aqueous electrons directly, and it can also remove dissolved oxygen in the system through a series of auto-oxidation reactions. By varying the concentrations and ratios of these reagents in the system, we can customize the UV photochemistry to handle a wide range of water chemistry parameters while still maintaining effective PFAS destruction. We can also modify the reaction chemistry to promote PFAS destruction under different operating conditions, such as batch or flow-through treatment modes. Our lab investigations for this work focused on 3 different objectives. Our first objective was to develop a flow-through system capable of destroying PFAS at an effective rate. Our second objective was to evaluate and optimize the robustness of the system by examining its ability to destroy PFAS in the presence of different common water co-contaminants. Our third objective was to apply the optimized system to destroy PFAS in a real-world PFAS-impacted sample. One of the other challenges in developing PFAS remediation technologies is ensuring you have a solid understanding of the PFAS present in your sample and how PFAS can transform over time. The gold standard for PFAS analysis involves the use of liquid chromatography tandem mass spectrometry, which identifies PFAS based on their molecular mass and their structure. There are several different EPA methods that utilize LCMS technology, including EPA 537, 533, and 1633. These methods differ by the matrix they are designed to analyze and by the numbers of PFAS the methods will analyze for. The most advanced of these methods, 1633, will identify a minimum of 40 different PFAS compounds, including a suite of perfluorosulfonic acids, carboxylic acids, fluorotelomers, and perfluoroethers. However, LCMS analysis is incapable of identifying any PFAS outside of that target list of compounds, which are often referred to as unknown or precursor PFAS. These unknown PFAS can include polyfluoroalkyl acids, which are often found in commercial products, industrial processes, and aqueous film-forming foam. Some examples of these include fluorotelomere sulfonamidobetanes, an example of this which is pictured. These unknown PFAS can also include PFAS transformation products, which are compounds that are formed during applied remediation technology. A classic transformation product found in the UV technology is shown here, which is the minus fluoride plus hydrogen exchange PFAS, in which a single carbon fluorine bond has been broken and replaced by a hydrogen atom. If, for example, you had a technology that converted 100% of your PFAS to an HF exchange PFAS, then 1633 would report that you would have a 100% loss of your original PFAS molecule. However, if you looked at your fluoride, you would only see a 6% reduction in the total organic fluorine load of your system. To analyze these unknown PFAS compounds, we can employ tools like the total oxidizable precursor assay, or the TOP assay, or high-resolution mass spectrometry. I will discuss the TOP assay and its applications towards the end of this presentation. I will first detail our initial lab development studies, optimizing the engineering of this Parsons patented technology. All the data presented here is patented. There are several different reactor types we employed, including small-scale cuvette reactors, large-scale batch reactors, and flow-through reactors pictured here. Each of these reactors have advantages and disadvantages inherent in their design. These small-scale cuvette reactors are great for investigating a wide range of variables at once and operates assuming the samples will undergo complete UV irradiation. However, the ideal nature of these cuvettes may result in them not being representative of a full-scale treatment system. The larger scale batch reactors are often more representative of a full-scale UV treatment system and can use physical mixers to compensate for incomplete UV irradiance. However, these reactors are limited with the volume of water they can treat at one time, and they can be difficult to implement on a larger scale. Flow-through reactors can often operate in continuous treatment mode and can use gravity or back pressure to control the flow rate through the system. However, these reactors can often suffer from overheating effects as all the light is captured in the reactor, as well as from the heat from the lamp itself. Furthermore, the materials used to create the flow-through reactor may not be compatible with the chemical environment required to destroy these organic pollutants under investigation. To address these issues, the first lab development challenge focused on creating a wrapped reactor system in which quartz tubes were wrapped around a UV lamp continuously and separated by air. The advantages of this system include higher control over mass and energy transfer, the ability to infuse any reagents at any location of the reaction, the separation of the lamp from the treatment solution mitigates fouling, and we can more easily implement tunable reactor geometry and maintain the system. Pictured here is myself holding the final pilot developed in our first year of investigation of 2024. And to reach this final design, two main variables were investigated: the distance of the quartz tubes themselves from the UV lamp, which is looking at the influence of UV energy, and the diameter or the width of the quartz tubes themselves, which is looking at the influence of UV penetration. And I hypothesized that as the distance and the diameter increased of the tubes and the distance from the lamp, we will see treatment rate decrease. However, treatment volume will increase. Before I jump into presenting the data, I would like to walk through some quick general interpretation. I will be presenting raw kinetic destruction data, represented as free fluoride, liberated from the destroyed PFAS. We use PFAS spiked water recirculated through our quartz reactors, and our samples are analyzed for free fluoride and triplicate in-house using our fluoride ion selective probe. I then relativize this fluoride data by dividing it by the initial organic fluorine concentrations that are determined via our 1633 analysis with LCMS through third-party commercial analysis. And this confirms and identifies the percent destruction of the PFAS compound. And our UV system follows a first-order rate determination. And we will be using this to compare across different treatment systems and variables. And the steeper the slope, the faster the PFAS are destroyed. So I first looked at the distance between the lamp and the reactors themselves. And I used a fixed diameter 25 millimeter wide quartz tube reactors and presented here. From left to right, we reached 90% destruction of PFAS after 2 hours running through the system. And when we increased the distance to 40 millimeters, it took 2.5 hours. And then when we increase the distance to 50 millimeters, it now takes 3 hours to reach 90% destruction of PFAS. We can process the data from each of our trials to calculate several key treatment parameters, including our energy efficiency, or EEO, our treatment rate in liters per hour, and our normalized treatment rate in liters per hour per cubic meter of reactor volume. And as we can see, our 30 millimeter distance reactor had the most energy efficient design at 29 kilowatt hours per cubic meter, and the fastest normalized treatment rate of 219 liters per hour per cubic meter of theoretical reactor space. And as hypothesized, increasing the distance did decrease the destruction rate, but increased treatment volume. However, considering the smaller footprint of the 30 millimeter system, it was identified the best among these variables. Next, I investigated the diameter of the tubes, or the width, using a fixed distance of 30 millimeters from the UV lamp. And we found that diameter had a significant effect on PFAS destruction rate, as we reached 90% PFAS destruction at 2 hours, again with our 25 millimeter diameter lamp, 4 hours when we increased the width to 30, and we only hit 85% destruction of PFAS at 6 hours when we increased the width to 34 millimeters. Once again, by taking the data from each of our trials and calculating the water treatment parameters, we can identify that the 25 millimeter internal diameter reactor, spaced 30 millimeters away from the UV lamp, was the most effective reactor. The other two diameters recently investigated had significant issues with UV light attenuation. As a follow-up investigation, I hypothesized that instead of investigating thicker diameters further away from the lamp, I should maybe investigate thinner reactors positioned as close to the lamp as possible, as this would maximize UV light saturation, with the main drawbacks being wasted UV light and energy and smaller treatment system volumes. However, these drawbacks can be easily compensated for down the road by using pre-concentration technologies. The initial reactor development identified an energy-efficient reactor design of 30 millimeter distance quartz tubes away from the lamp with 25 millimeter of width tubes. However, I hypothesized that a more compact reactor design closer to the lamp with thinner diameter tubes may result in an even faster PFAS destruction rate. And pictured here is the more compact reactor with 10 millimeter internal diameter of quartz tubes. They were purchased and connected in series using 3D printed Elmos and polymer sealants. And our initial investigations with our more compact tubulator reactor identified that it destroyed PFAS rapidly, achieving over 90% destruction of PFAS in half an hour, compared to the 2 hours in our more previous efficient reactor. However, as predicted, the reactors are too small to absorb all the UV light, resulting in some energy being wasted and a lower overall energy efficiency of 110 kilowatt hours per meter cubed versus 30 kilowatt hours per meter cubed in the previous reactor. This reactor is best suited for applications in which rapid PFAS destruction is prioritized over energy efficiency. Given that there are many ways to improve energy efficiency, including the use of pre-concentration technologies, the advantages of this tubulator reactor outweigh its disadvantages. Pictured here is our evaluation of our 2024 flow-through reactor on the top compared to our 2025 reactor. As we can see, the 2024 reactor was able to achieve 90% destruction of PFAS with a single photochemical reactor with a treatment time of 1 liter per hour. However, the 2024 reactor did struggle with poor flow profile control, resulting in an initial lag period in which PFAS destruction was between 60 and 80%. Following several iterative improvements, we optimized the reactor in 2025, achieving a PFAS destruction rate of over 99% sustained in a single photoreactor treatment rate of 2 liters per hour, and resolving the initial issues surrounding our flow profile. As we continue to improve and optimize our photoreactors, we expect to see further improvements to the treatment rate as well as improvements to the overall energy efficiency of the reactor. Next, I will jump into our initial lab development studies, focusing on the chemistry sides. I focused on investigating the impact of co-contaminants, as our initial technology development trials focused on PFAS-spiked deionized water, so very clean. To evaluate the robustness of the catalyzed UV system, PFAS destruction was evaluated in the presence of several different inorganic and organic contaminants. I hypothesized that co-contaminants that would interfere with reducing radicals, for example, nitrate, or would inhibit UV penetration, for example, suspended solids, would have the biggest impact on lowering PFAS destruction. Several salts were evaluated, including sodium phosphate, sodium sulfate, sodium chloride, sodium carbonate, and sodium nitrate. And pictured on the top, we have our sodium sulfate results. Most salts had little to no impact on PFAS destruction, indicating PFAS destruction can be achieved under high ionic strength conditions. However, as predicted, nitrate did have the most significant impact due to the quenching of aqueous electrons, and a concentration of about 10 millimolar nitrate pretty much killed the efficacy of our system, and 1,000 millimolar of sulfate didn't do much of it to lower the efficacy at all. We also looked at the impact of metals, and the main metal investigated was iron sulfate. And pictured here, we investigated concentration of up to 200 millimolar. Found the solution became increasingly turbid with increasing iron concentration due to the formation of iron hydroxide under the alkaline conditions. Results identified that while PFAS destruction can be achieved at iron concentrations under 10 millimolar, pretreatment will be required for higher containing iron matrices. And we would expect similar trends for other metals. We also looked at the impact of humic acid, and it was investigated as a model natural organic matter contaminant. Similar to iron, the solution became increasingly turbid with increasing humic acid concentrations, and we investigated all the way up to 1,000 milligrams per liter. Humic acid was partially degraded using the catalyzed UV system. However, PFAS degradation was still significantly inhibited at humic acid concentrations of above 25 milligrams per liter. We also looked at investigating the impact of several different quaternary ammonium salts, as industrial processes can often contain quaternary ammonium salts and surfactants. 3 common compounds were investigated: butyl ammonium chloride, or BAC, tetrabutyl ammonium chloride, or TBAC, and cetyl trimethyl ammonium bromide, or CTAB. And we have the back and the T-back results pictured here. As you can see, the placement of the ammonium functional group is very important for whether the system is affected. The unshielded ammonium in the back rapidly quenched the aqueous electrons, significantly impacting PFAS destruction at even 1 millimolar, and certainly up to 5 millimolar. And we see in shielded ammonium in the T-back pictured on the bottom, we see that it's not able to quench aqueous electrons as effectively, as it only mildly impacted PFAS destruction. And 25 millimolar, we're still seeing great PFAS destruction. We also looked at the impact of CTAB, which is a quaternary ammonium surfactant that is used regularly for disinfection applications. It is also commonly used in PFAS remediation technologies as either a foaming agent for foam fractionation or as a micelle forming agent to concentrate the PFAS. We found interesting results that we found that CTAB had an inverse impact on PFAS destruction as an effect of concentration. We found that very low concentrations of CTAB significantly stopped PFAS destruction, around 1 millimolar, and increasing CTAB concentration further increased PFAS destruction. We almost hit full destruction at 50 millimolar, which suggests that CTAB could potentially improve PFAS destruction in complex matrices, but would require significant investigations to identify the optimal application. And here we have a summary of all the co-contaminants that were investigated. And we found that the most impactful co-contaminants that were identified were nitrate, quaternary ammonium salts, humic acid, and metals. And these results identify that for specific matrices, sample pretreatment may be necessary. Fortunately, there are technologies to remove metals, nitrate, and organic matter, and they're readily available and mature on the market. Next, I will jump into presenting our data validating the destruction of PFAS in complex matrices. For the characterization of our AFFF rinsate and the subsequent destruction, we employed 3 complementary analytical techniques. EPA 1633 performed using LC-MS, the total oxidizable precursor assay, or the TOP assay, and the total fluorine, total organic fluorine assays. The LC-MS analysis quantifies a targeted list of PFAS based on the method employed and the available analytical standards. For EPA 1633, this focuses on 40 PFAS, including PFCAs, PFSAs, fluorotelomers, and perfluoroether acids. While using LC-MS analysis allows for the determination of the presence or absence of PFAS, it can't identify if PFAS in the EPA list have been completely destroyed or simply transformed into a new, different PFAS that isn't present on the method list. And to fill in this gap, the TOP assay oxidatively converts polyfluorinated compounds not present in the 1633 list into terminal PFCAs, which are present on the list and are easily detectable using your standard 1633 LC-MS analysis. The TOP assay allows for the semi-quantification of unknown PFAS compounds and is very useful for providing an estimation as to the initial PFAS concentrations present within a sample. However, the effectiveness of the TOP assay can be impacted by highly complex matrices and can often underreport overall PFAS concentrations. The total fluorine and total organic fluoride assays destructively convert all fluorinated species into free fluoride, which are then easily quantified using a fluoride ion selective electrode or ion chromatography. These fluoride analytical methods are great at accurately identifying the presence of fluoride and evaluating its transformation over the course of PFAS remediation, but the techniques are still under development, and non-PFAS compounds like PTFE or high background inorganic fluoride concentrations can convolute results. We characterize our PFAS-impacted AFFF rinsate through 3 different analytical methods. The first characterization was on an unprocessed, simply diluted sample of the AFFF rinsate, which was characterized using method 1633 at a commercial laboratory. The second characterization was on a sample that was subjected to a UV-activated top assay that was performed in-house in the Syracuse lab, and then sent out to a commercial laboratory for analysis using 1633. And our third characterization was focused on identifying the total organic fluorine concentrations in-house using our UV-based destructive technique that has been published in literature. The initial analysis of AFFF rinsate by 1633 only identified around 5 milligrams per liter of organic fluoride, as pictured here on the very left bar, consisting mainly of PFAS and PFH excess. Following the application of the top assay, the PFAS concentration was revealed to be increased rapidly to 71 milligrams per liter of organic fluoride, and this consisted mainly of PFH-PA and PFH-XA. This tells us that not only is the AFFF made of mainly PFAS precursors and not PFAS or PFH-XS, but the PFAS precursors also follow a C6 fluorotelmer formulation, as is shown by the formation of PFH-PA and PFH-XA in the post-oxidation samples. Lastly, in our third bar here, our in-house total organic fluoride analysis identified 81 milligrams per liter of organic fluoride, as shown in the graph on the right, as well as 15 milligrams of background inorganic fluoride, which is not depicted here. Following the initial characterization of the sample, we subjected the AFFF rinsate to the Catalyzed UV destruction technology and sent it out the post-UV destructive samples and the pre to the same commercial laboratory for analysis. Compared to an initial PFAS concentration of over 100 milligrams per liter, which is the equivalent to 71 milligrams per liter of organic fluorine, only 0.031 milligrams per liter of PFAS remained after treatment. This demonstrates that the catalyzed UV technology achieved a 99.9997% destruction of the PFAS present. However, as we discussed earlier, we need multiple lines of evidence of analytical evidence to support any claims of PFAS destruction. For this, we can examine our fluorine mass balance in our pre- and our post-treatment stages. To reiterate, our initial characterization of our AFFF rinsate identified 71 milligrams per liter of organic fluorine determined in our post-top assay samples using LCMS, and 81 milligrams per liter of organic fluorine determined using our in-house total organic fluorine assay, which determines the organic fluorine concentration using a fluoride ion selective electrode. In our post-treatment samples, we identified less than 0.03 milligrams per liter of organic fluorine and 76 milligrams per liter of inorganic liberated free fluoride determined using a fluoride ion selectrode. The amount of inorganic fluoride recovered was slightly higher than expected based on our LCMS analysis of 71, but it was also slightly lower than based on our TOF analysis of 81. When considering the standard deviation of our samples across our different analytical techniques, we identified a fluoride mass balance or total PFAS destruction of 107 plus or minus 6% based on LCMS data, and 95 plus or minus 12% based on our TOF assay data. Overall, these results identify that the catalyzed UV technology is capable of achieving destruction of PFAS in complex matrices, with over 99.999% destruction based on LCMS analysis and near complete closure of the fluorine mass balance. As analytical methodologies continue to develop and we evaluate this technology on increasingly complex matrices, we will continue to evaluate PFAS destruction using this multiple lines of evidence approach and prioritize complete fluoride mass balance closure. And to wrap up with our conclusions and future steps. To conclude our presentation today, I've achieved 4 key objectives across the technology development of our Parsons patented catalyzed UV. We have identified the destruction of PFAS in an optimized flow-through reactor, identifying the key geometry considerations and their impacts on treatment rate and energy efficiency. We have demonstrated the destruction of PFAS in the presence of several organic and inorganic matrix components, identifying which parameters are the most impactful on inhibiting PFAS destruction and allowing us to identify methods to compensate for any losses in efficacy. We've also demonstrated using a multiple lines of evidence approach the destruction of PFAS in complex AFFF impacted real-world samples. And lastly, we have confirmed PFAS destruction through the investigation and closure of the fluoride mass balance. Based on our developments and the data presented today, we've identified that the Catalyzed UV technology is a promising tool for the remediation of PFAS-impacted aqueous matrices and will be suitable for applications to groundwater, landfill leachate, industrial wastewater, AFFF rinsates, and other complex samples. And I would like to thank the following for their contributions in supporting research and development, management, experimental design, analytical, and for field demonstration. I'd like to thank Dan Griffiths, David Patch, Lauren Turner, Emily Crownover, and Ryan Thomas. I would also like to thank everyone present today for taking time out of their day to come listen to me present, and I'd be happy to take any questions.
Thank you, Natalia. That was a great presentation on some of the latest research in defluorination of PFAS. These are some really exciting results to see. If there's any questions, you can either raise your hand to ask it live, chat at any time. It looks like there's already a few that have come up. So the first question is, what were the initial spiked PFAS concentrations for these reactors?
The initial concentration was around 5 milligrams per liter or 5 ppm, sometimes 10.
Next question is, what wattage UV bulbs were used for the evaluation, and will a new study be conducted to evaluate different wattages versus treatment efficiencies?
To answer the last part, yes, we will be looking and investigating more wattages, and the wattages depends on the size of the treatment system. So the smaller scale cuvette reactors used a 36 watt lamp, and our larger scale flow through reactors use a higher power, larger 55 watt lamp.
Okay, so were UV light reflectors surrounding the reactor tubes considered to increase efficiency? Heat dissipation by air would be restricted.
Yes, we have been investigating that, and we have been investigating several different types of reflectors to contain and utilize the most of our UV light. And we do also have to investigate the balance of heat. And we will be looking more into that in the coming year.
Okay, the next question is, regarding the reactor layout and the flow issues mentioned, have you considered using a single spiral quartz tube rather than a bunch of straight segments with elbows? It might be more expensive, but I'd assume the flow would be smoother. Plus, if you run the flow upward through the spiral, it might be able to flush air out of the lines by itself when starting up.
Yeah, great suggestion. We are investigating many areas of reactor design and improvement.
Okay, next question is, what steps do you think could be taken for treating PFAS impacted samples that have high concentrations of organic matter?
We would be looking at using pre-oxidation steps to clean up beforehand, and we're also looking at using ion exchange resins as well.
Let's figure out another question here. The results presented are based around a single UV photoreactor. Could multiple photoreactors be combined together?
Yes, yes, they certainly can, and that is the plan for 2026.
If there's any other questions, you can certainly raise your hand or enter in the chat at this time. Guess we can go to the next slide for.
Actually, do
Oh,
you mind
yep.
if I ask a question out loud? I think a couple of
Go
us
for it.
raised their hands. Thanks for that presentation, Natalia. I was curious if you could talk some about how and if this technology would be good as like a treatment train approach. Like, could we combine this with other technologies for PFAS
Yes.
treatment?
Yes, thank you, Christy. That's a fantastic suggestion. And yes, this technology would be perfect to be integrated into a treatment train. And we're looking at integrating that into several different systems for the next year.
Are there any in particular that make sense for combination? I don't know. Like, do you need other pre-treatment ahead of time
Yes,
before
we're
this
looking at,
technology? So would you be doing other technologies ahead of this technology more so, or the other direction? Would you do this technology first and then look for something after?
we would probably use this as the more on the final end of the treatment train. And it always would be dependent on the matrix coming in. We've received some landfill leachates recently that are quite clean and require no pre-treatment. And then there's some landfill leachates that are quite nasty and other types of matrices. So it's always depending on the matrix. And we would look at investigating several different pre-treatment steps in series, such as oxidation and RO and ion exchange resins to concentrate and pull our PFAS into a very more concentrate and clean waste stream.
That's
and then
awesome.
Yes, and then end it off with our reduction system.
Yeah, since you're getting down to really like not detect levels, it definitely makes sense that this technology could be the final polishing step.
Yep.
Thanks.
Hey there, Natalia. Fantastic presentation. Honestly, really great job. Well done. Can you explain the role of dissolved oxygen and pH in your water chemistry? Is that a big concern? And if so, how are you dealing with it?
Thank you, David. Excellent question. Yes, it is a concern with aqueous electrons. One of our main scavengers of aqueous electrons in our systems will be oxygen and free protons. So we do have this system at a very basic pH. It's around 13.2, and we like to keep it very basic to prevent any aqueous electron scavenging from protons. And we also like that we utilize the sulfites chemistry of auto-oxidation reactions to lower our oxygen and minimize any oxygen entering our system to reduce the scavenging from oxygen side as well for aqueous electrons. Thank you.
Looks like we have another question in the chat. Is this system applicable to other contaminants for use at sites where there are PFAS and non-PFAS co-contaminants?
Yes, I do believe it will be applicable. Following certain investigations, as depicted, there will be some co-contaminants that we may have to pre-treat or do extra modifications of the system to handle. But I do believe, yeah, extra PFAS can be handled alongside extra co-contaminants as well.
There's another question. Can you explain why iron interferes with the effectiveness of the system?
We believe that iron interferes primarily through turbidity. As the actually in one of the pictures, actually in the first co-contaminant picture with the cuvettes with all the nasty like blue flocky stuff, that is the iron. So we found that the iron precipitated due to our basic conditions in our system, and created quite turbid conditions, and the UV light simply couldn't penetrate and reach our photochemical reagents and activate them.
So there's another question. As a follow-up to the iron question, can you explain why nitrate has such a strong ability to interfere?
Nitrate has a very high bimolecular reaction rate, and the aqueous electrons will preferentially want to react with nitrate over PFAS, especially due to the positive charge as well.
Do you think foam fractionation can be a step toward before the UV treatment in a larger scale system?
Yes, we are looking at utilizing foam fractionation to help increase the efficiency of the system by concentrating massive amounts of water into highly concentrate waste streams, as due to the system can operate on a first order reaction. So as long as the concentration isn't so high that the PFAS are forming micelles on itself, this system can handle very high concentrations of PFAS. So foam fractionation is an excellent front end step to complement for the system.
Okay, the next question is, would another metal source like copper be a better reagent?
Not particular. We would expect the same results with copper as well.
Is there maybe any cost efficiency, or they're kind of roughly the same ballpark?
Yeah, it would be the same. We don't really have much of a use for copper in this system.
Let's see. The next question is, are there concerns over dissolved oxygen or pH having an impact on PFAS destruction?
Yes, more basic. If we did have more acidic conditions with more free floating protons, that would scavenge our aqueous electrons and lower the amount that would be left over for PFAS, and then lowering the efficacy of our destruction. And the same would happen for oxygen as well, and other aqueous electron scavengers.
Okay, the next question is, can you go back to your sulfite and iodide chemistry formula slide and explain the regeneration step?
Okay, so when iodide is activated by UV light, it will produce the iodide radical and will eject an aqueous electron. However, once it's been converted to this radical, it is now spent and it can no longer be activated to generate more aqueous electrons. However, sulfite can be used in this process, as the sulfite, which acts as the sacrificial catalyst, can regenerate the iodide radical by reacting with it and restoring it back to its original iodide minus properties. And then the UV light can then hit it again, where it will eject another aqueous electron and it will then turn back into an iodine radical, and the sulfite will then continue to regenerate it. So the sulfite does get used and spent up in this process, as it's the sacrificial catalyst. So one of the main optimizations with this system is to continue to add more sulfite if we have more recalcitrant PFAS to destroy. So if we have a PFAS compound like PFBS, for example, PFBS does require extra sulfite additions to overcome the recalcitrance of the compound, and we need to run this reaction for longer. So to run this reaction for longer at the same efficiency, we would just keep adding sulfite so that the iodide radical can continue to regenerate itself.
Okay, we got one more question right now in the chat. Is this technology reliable? Will it disassemble components and generate new ones that weren't taken into account? And when would it be commercially available?
Yes, we believe this technology is quite reliable. We've demonstrated many validation data to prove that it is reliable and it works. We are just confirming any background disinfection products, but we're not too worried about that. We can work with that, and we would like to eventually get this to market. Yes.
There's also a question of what would the estimated cost of technology per cubic meter be, but I'm guessing that you're not quite at that stage yet.
Yeah, that is more of a focus on 2026 when we are focusing on more on the field deployment and for next year. So I'll be able to get you more of an answer in the future.
Our next question is, what do you see as the primary hurdles with upscaling to the industrial or commercial scale? What are the primary applications, for example, municipal drinking water or wastewater?
Those primary hurdles are going to be the focus of 2026. However, we have been working on some of them, which is just the stability, keeping the system, the stability of the system and maintaining flow profile. And those would probably be our biggest issues, as the primary applications are a broad range of aqueous matrices.
Another question just came in, was the flow-through system operated in a recirculation mode? If switching to a single pass mode, which represents a more realistic application, how would the PFAS destruction efficiency change and how would you address that?
So we utilized both recirculating and flow through. So in the engineering development of the section that I was presenting, that data was used in a recirculating method. So we can easily investigate the diameters without actually having to build an entire reactor every single time, which would be quite labor and materials expense. And then when we confirmed and kind of and focused more on and confirmed our final reactor design and we're confident with the efficacy and our improvements, then we built and actually constructed two different reactors, the energy efficient one and the more compact one, and we have ran both of them in flow through mode.
We can maybe go back to the final slide for next month's webinar. Okay, so our next webinar will be on September 10th on innovative pilot testing for bioremediation of chlorinated VOCs in overburden and metamorphic bedrock groundwater. So we presented by Hannah Annunziata and Jim Schutz at the same time as today's webinar, 12:30 to 1:30 p.m. Eastern Time. A link to the form for pH credit has been posted a few times during today's webinar in the chat. If you had any issues, please contact us and we'll get you that form. And if you missed any of the questions or content, the recording of this webinar will be posted on our YouTube channel in the next few days to a week. Thank you to everyone who joined us for today's webinar, and we hope to see you again in September.